Drift into the quiet edge of a black hole where light bends into thin rings, shadows hold steady, and the universe reveals its limits without a single sound. In this sleep documentary journey, the story follows what can be observed near an event horizon and what must remain unknowable. If this calm science atmosphere helps you relax, please tap like and subscribe for more long-form cosmic sleep stories. Turn on notifications so the next Deep Space episode is ready whenever the night is. A boundary can exist without a wall, and a black hole shows that boundary with its unusual clarity. The event horizon is the edge where escape by light ceases to be possible. In that region, leaving is not a matter of speed. Leaving is a matter of what paths exist at all. The opening image stays quiet and steady. A dark circle sits in a dense star field. A thin veil of gas drifts nearby in slow layered sheets. Faint rays from distant stars pass the darkness and bend into gentle curves. Some rays swing wide and continue outward. Other rays tighten into arcs that skim close and vanish from view. A first payoff settles into place. A black hole is defined by a boundary in space-time, not by a visible surface. That boundary is where the future itself no longer includes an outward route for light. A simple definition holds the core without heavy machinery. An event horizon is a one-way boundary for signals. A signal would be any change that could travel outward, even a brief brightening in thin gas. Outside the boundary, at least one outward route remains available. Inside the boundary, every future route points inward instead. The next visual anchor slows into motion near the edge. A narrow filament of gas spirals toward the dark center. It brightens slightly as it compresses and heats. It does not strike a shell or bounce back. It simply passes the boundary and continues inward. The outside still receives light from the filament for a time. That light comes from the region just outside the edge. The edge itself stays silent. Scale can be anchored with a single safe number. For a black hole with the mass of the Sun, the horizon radius is about 3 kilometers. That span is like the width of a broad valley between two ridges. It is small compared with the size of a star, yet it marks a change in what the outside can ever learn. 3 kilometers can also separate events that can affect distant space from events that cannot. The boundary is small in distance and immense in consequence. A new payoff follows from that contrast. The horizon is near in length and far in reachable information. To make that idea concrete, space is treated as a landscape of possible directions. A light cone is the set of possible light directions. In plain language, it is the local spread of where light can go next. In calm gravity, that spread includes many outward directions. Near the horizon, that spread tilts inward. It tilts until outward directions stop appearing at all. The visual anchor shifts to a slow drift of glowing dust grains around the dark center. Far from the edge, some light from each grain moves outward and escapes. Closer to the edge, outward-going rays are bent back and fail to leave. A quiet payoff clarifies what the bend means. The horizon is not a surface that blocks light. It is a region where outward paths cease to exist as future options. A calm limit of intuition appears here, and it deserves a clear name. Ordinary intuition treats space and time as separate. Near the horizon, that split misleads. The limit of intuition is that straight ahead stops being a global idea. A route that begins outward can still end inward. The limit of observation is cleaner and more final. No information that starts inside the horizon can reach the outside later. This limit is not a weakness of weighting or of precision. It is built into the structure of allowed light paths. The visual anchor becomes a thin pulse of brightness that travels along the filament. Outside the edge, the pulse can send part of its pattern outward. Inside the edge, the pulse can only carry its pattern deeper inward. A payoff settles like a soft latch. The horizon is the boundary of what can influence faraway regions in the future. Another payoff arrives by separating the boundary from the central interior. The horizon is not the place where matter must become infinitely dense. The horizon exists even if interior details remain uncertain. It is a boundary of causality, not a boundary of substance. The scene widens to show this difference in a physical way. A faint disk of gas circles in broad loops far from the centre. Closer in, the loops tighten into faster paths. The disk shows layers and streaks shaped by shear. That shear is a concrete detail. It creates clumps and it stirs heat. Light from those clumps is what becomes visible at great distances. The horizon remains a concept inferred from what light cannot do. The glow carries a further lesson about what observation can and cannot isolate. What appears near a black hole is almost always the environment outside the edge. Light from the gas is redirected by curvature around the boundary. Some rays leave directly from the bright side of the disk. Some rays skim close to the edge. They curve around and leave later. A small payoff clarifies the consequence. One physical region can send light along many path lengths. Arrival time can spread out even when emission is brief. The visual anchor becomes a set of faint arcs around the dark centre. Each arc is the same source seen along a different bent route. This is where observation meets a practical limit. Finite resolution blurs narrow features. Scattering in hot gas can smear light into a softer glow. The exact location of the horizon cannot be drawn as a sharp line from images alone. It must be inferred from the consistent patterns in bending and disappearance. A final concrete detail grounds the boundary in shape without adding extra terms. For a non-rotating black hole, the horizon is spherical. For a spinning black hole, the horizon becomes slightly distorted. The distortion is smooth and continuous. It has no texture that light can reveal from outside. What can be seen is a shadow-like deficit framed by curved light. The closing image slows again. The starfield holds nearly still. The dark centre remains featureless. A thin crescent of emission drifts along the inner edge of the disk. The calm promise becomes clear. The boundary sets strict limits on observation, and the neighbourhood just outside it offers the clues. The next step follows the idea of escape turning into geometry and the paths that fail one by one. Escape looks like an everyday idea until gravity reshapes what outward even means. Near a black hole, escape becomes a question of available paths rather than effort. At this distance, space is calm and open. Light behaves as straight motion through a wide ski. A faint ribbon of gas glows and drifts across a starfield. Its glow sends rays in many directions. Some rays leave and spread into the dark. Some rays cross behind the central darkness and still return outward later. A small payoff settles quietly. Far away outward is a broad set of directions. Escape is still a geometric possibility. The primary visual anchor forms as a pale dome of starlight above the glowing ribbon. The dome is not a surface. It is an imagined sky of directions. Rays rise through that dome like thin chalk lines. In that region, half the sky leads outward in the long run. Half the sky is like half of a bowl held overhead. It is a simple measure of how many directions can carry a signal away. Closer in, the bowl changes shape. The rim of the bowl tilts. The slice of directions that truly lead outward shrinks. Another payoff arrives in plain terms. The horizon is reached when that outward slice closes completely. A new term appears once and then returns to ordinary words. An escape cone is the set of outward light directions. It is a cone in direction space, not a physical tunnel. Like a patch of clear sky between clouds, it marks where a ray can still rise away. Like a narrowing gap in reeds, it shows which angles still allow passage. It matters because visibility depends on those angles. The scene tightens around the glowing ribbon. The gas thins into layered sheets. The layers shear past each other in slow gradients. Bright knots form and fade along the inner edge. Each knot sends light outward in a spread. Light from the side facing outward has a better chance to leave. Light from the inward side is bent back. A small payoff clicks into place. Even before the horizon, many rays that start outward still fail. The failure is not a collision. It is a bending of the path until the ray returns inward. The primary analogy enters with a calm, natural image. The region behaves like a river current approaching a wide waterfall. Far upstream, a leaf can drift in many directions. Near the lip, the current aligns everything downstream. Even a leaf pointed upstream is still carried forward by the flow. In that region, gravity plays the role of the current. The current is not a force that grabs light. It is the shape of space-time that guides every future direction. The analogy stays gentle and concrete. The lip of the waterfall is the horizon. It is where every future path is carried inward. A visual anchor repeats in a new form. Dust grains glow briefly as they pass through thin, heated layers. Each grain is a tiny lantern in motion. Its light spreads like a soft halo. Far from the edge, the halo contributes to the outward sky. Closer in, the halo is clipped into a narrow fan. Another payoff follows without strain. The shrinking fan is the escape cone narrowing. The narrowing happens smoothly. There is no alarm line. There is only a steady reduction in outward options. The scale shift is quiet and deliberate. The change is described in angles and directions which are small and local, yet the consequence is cosmic and global. A tiny change in which way a ray points decides whether a signal reaches far space. One moment becomes a difference across thousands of years of travel time. In that region, a ray that fails does not vanish instantly. It curves and lingers. It can circle partway around before it falls inward. That lingering shapes what the outside can receive. A small payoff lands softly. The horizon is not where light stops moving. Light still moves at the local limit. The horizon is where outward motion no longer exists as a future direction. A limit of observation enters here with a clear edge. No measurement can trace a single ray from inside the horizon back out. This is not a problem of sensitivity. It is a problem of allowed paths. The best that observation can do is infer the boundary from what fails to return. The inference is indirect. It depends on models of bending and on how bright structures smear in gas. The limit is also practical. Finite resolution blurs the region where the escape cone becomes very thin. Scattering in hot plasma can soften sharp features into haze. The boundary is approached through patterns, not by touching a line. The visual anchor shifts to a slow pulse travelling along the ribbon again. The pulse is a gentle brightening, then dimming. Far from the centre, a signal would send part of that pulse outward with little distortion. Closer in, the outward part is reduced. The pulse becomes weaker in outward directions. A small payoff clears a common confusion. The pulse does not fail because it lacks power. It fails because fewer directions remain open. Another physical detail grounds the geometry in motion. The inner layers of the disk move faster than the outer layers. That speed gradient stretches bright clumps into streaks. The streaks arc around the darkness like painted strokes on a spinning wheel. Light from those streaks is bent. Some rays skim close and wrap around. Others leave directly. The escape cone decides which is which. The river analogy deepens without adding new terms. Upstream, the water allows side channels and eddies. Near the lip, side channels disappear. Eddies are pulled tight into the main flow. Likewise, far away, outward directions are abundant. Near the horizon, outward directions thin to none. The payoff is immediate and calming. Escape becomes a property of space-time, not of the emitter. Even a perfect flash inside the boundary cannot send news outward later. The closing image widens slightly. The star field returns as a quiet background. The glowing ribbon remains outside the edge and it still sends some light away. The dark centre stays featureless. The transition stays soft and forward. The next step follows rays that almost escape in the fragile ring where light can briefly circle before it chooses a fate. Some light near a black hole almost escapes, yet chooses to circle once before leaving. The photon sphere is a fragile ring region where light can loop briefly, then either depart or fall inward. In that region, the scene grows precise and spare. A dark centre sits inside a faint glow. Around it, a thin, luminous ring forms like a narrow band painted on deep night. The band is not matter. It is light that has been bent into near circles. Light behaves as paths that curve with space-time. A ray that would travel straight far away becomes an arc here. A first payoff settles into place. The bright ring is not an edge of the black hole. It is a map of routes that linger near it. The primary visual anchor holds steady. A single bright knot in the disk sends out a brief flash. Most of that flash leaves along many directions. A small part swings close to the centre and turns. It wraps around and leaves later. The delayed glow arrives as a thinner echo of the first. The ring looks sharper where many such delayed paths overlap. The physical detail stays concrete. The ring is narrow because the allowed angles are narrow. The curvature is strong and the turning happens over a short distance. One number can anchor that distance without strain. The photon sphere lies at about 1.5 times the horizon radius. That factor is like adding one extra step for every 2 steps already taken. It is close enough to feel immediate. It is far enough to change what a ray can do. The payoff is quiet and direct. Light can circle outside the horizon without touching it, yet the margin is small and delicate. A new term appears once and then returns to plain language. A null geodesic is a path of light in curved space-time. In plain language, it is the route a light ray naturally follows. Like a bead sliding on a smooth curved glass rim, it follows the shape without needing a push. Like a drop tracing a groove on a leaf, it stays on the channel while the channel lasts. It matters because the ring of light is made of such routes. The scene shifts to slow motion in the inner glow. A haze of hot gas drifts in layered sheets. Its brightness has gradients. The side closer to the center brightens and fades with small ripples. Each ripple sends rays outward. Some rays leave quickly, some rays skim the turning region and loop. A payoff arrives with the loop itself. A loop does not guarantee capture. A loop can be only a brief delay. The delay depends on how close the ray comes to the fragile ring region. Rays that pass a little farther out bend less and depart sooner. Rays that pass a little farther in bend more and fail to depart at all. The limit of intuition begins here and it needs a clean statement. The photon sphere is not a stable orbit for light. It cannot hold a ray for long without perfect aiming. A tiny change in angle decides the outcome. That tiny change is smaller than most instincts expect. The ring region behaves like a knife-edge balance. It holds only in the narrow sense. The primary analogy stays gentle and new. The turning region is like a thin ridge on a dune where sand grains can slide either side. On the crest motion can linger. A slight drift sends a grain down one slope. Likewise, a ray aimed just right can circle briefly. A ray aimed slightly off will either peel away or spiral inward. The payoff is immediate. The ring marks a boundary of stability, not a boundary of space. A second visual anchor arrives within the same main scene. The luminous ring thickens in places and thins in others. The thickening is caused by many rays spending extra time in similar loops. The thinning is caused by fewer rays sharing that delay. The ring can look like a fine thread. It can also look like a soft band when the environment scatters light. This is where observation meets its limit. No outside view can track a single ray through multiple loops. The loops are too close together in angle. The region is too compact in size. Finite resolution blends nearby paths into one glow. Scattering in hot plasma further smooths fine structure into haze. The limit of observation is that only statistical patterns are visible, not individual routes. The payoff follows from that constraint. The photon sphere is inferred from the shape of brightness not directly traced. Scale shifts again, this time from local loops to wide consequences. A brief looping delay near the center can translate into a long difference in arrival time far away. A faint echo can arrive after the main flash. The echo is dimmer and more stretched. The outside receives not one clean signal but a softened sequence. The ring of light is therefore a filter. It reshapes short events into longer patterns. The physical detail stays tangible. The ring's width depends on the sharpness of angles that can linger. The ring's brightness depends on how much glowing material is nearby to provide rays. The ring's smoothness depends on how much scattering exists between emission and departure. A small payoff clarifies what can and cannot be learned. The ring says much about geometry. It says less about the interior. The interior remains hidden by the horizon. The ring remains outside and visible. Another payoff arises by separating two kinds of darkness. The horizon is the boundary of no return. The shadow is a wider region of missing rays. Rays that would have reached the outside are instead bent inward. The turning region contributes to that missing set. It creates a silhouette that is larger than the horizon itself. The visual anchor deepens. The dark center looks like a clean disk. The ring traces a narrow rim around it. Farther out, a faint glow from the disk spreads in soft gradients. The entire pattern is shaped by rays that bend and loop. The limit of intuition returns with a soft boundary. Ordinary thinking imagines a ray as a straight arrow. Near the turning region, the arrow becomes a curve. The curve can wrap around and still depart. Yet the wrap does not mean the ray is trapped in a neat circle. It is a brief hesitation in a landscape of directions. The payoff is calm. The ring is made by hesitation. It is made by paths that almost fail to escape but still do. The closing image eases outward. The ring becomes thinner as the scene widens. The starfield straightens into calmer lines. The black hole's influence remains, but it becomes a gentle distortion rather than a tight loop. The transition turns softly toward the next step. Light that loops near the center also leaves with its color and timing changed. The next movement follows how signals stretch and fade as gravity shifts their frequencies and spacing. Color can drift without any paint mixing simply because gravity changes how light carries time. Gravitational redshift is the steady loss of light frequency as it climbs away from deep curvature. In that region, a thin sheet of gas glows with a clean gradient. The inner edge shines hotter and sharper. The outer edge is dimmer and softer. Light behaves as waves whose crests mark a rhythm. Near the black hole, that rhythm is set by local time. Farther out, the same crests arrive spaced farther apart. A small payoff settles immediately. The light does not lose speed. It loses frequency because space-time stretches the wave on the way out. The primary visual anchor forms as a narrow ribbon of color around the darkness. Close in, the ribbon carries a bluish tint. Farther out, the same kind of glow leans toward red. The ribbon is not uniform. It has patches and streaks shaped by shear in the gas. Each patch sends light upward through curved space. The upward journey is quiet but decisive. Every step outward slightly reduces the wave's frequency. The effect is cumulative and smooth. A new term appears once and then returns to plain language. Gravitational redshift is a shift to lower frequency and stronger gravity. Like ocean swells leaving a fast current and entering calmer water, the spacing between crests grows. Like a spring that relaxes and lengthens, the pattern stretches while the pattern stays continuous. It matters because color becomes a clue to how deep the light originates. The scene slows on a single bright knot in the inner layer. The knot brightens and then fades. Its glow sends a brief packet of waves outward. The packet starts with tight spacing between crests. As it climbs, the crests spread. The packet arrives with longer spacing and lower energy per wave. A small payoff lands softly. Energy is carried in the frequency of light. When frequency drops, the light arrives less energetic. One number can anchor the scale without strain. From near the photon sphere, the frequency arriving far away can be about half the emitted value. That is like wave crests ending up about twice as far apart. The change is not a sharp jump. It is a steady stretching. It grows stronger as the origin moves closer to the horizon. The physical detail stays tangible. The inner gas layer shows a steep brightness gradient. A narrow band near the center looks sharp and high contrast. The same band looks muted after it travels outward. The muted appearance is not only distance, it is the redshift reducing the energy per photon. A second visual anchor appears in a calm form. A faint ring of glow surrounds the dark center. Its inner rim is bright. Its outer rim is dim. The inner rim also appears shifted toward lower frequency when viewed from far away. The ring therefore looks both darker and redder than local conditions would suggest. A small payoff clicks into place. Redshift is a filter that dims as it shifts. Deeper origins are harder to see not only because fewer rays escape, they also arrive with less energy per photon. The scale shift is gentle and wide. Locally, the change is a subtle stretch in wave spacing. Far away, the same change alters the entire balance of what wavelengths dominate a scene. Over a short travel time, the packet's rhythm loosens. Over vast distances, that loosening becomes an enduring color bias in the received light. The calm mechanism also reshapes timing. A packet whose waves spread also carries less power per moment when it arrives. The glow seems to relax as it climbs. A small payoff clarifies a common confusion. The shift is not caused by the gas cooling during travel. It is caused by gravitational time running at different rates along the route. The primary analogy stays steady with a new everyday image. The effect is like ripples leaving deep water and entering a broad, shallow bay. The crest spacing changes smoothly as the environment changes. Nothing needs to push the ripple backward. The bay simply sets a different relationship between distance and wave rhythm. Likewise, space-time sets a different relationship between time and wave rhythm at different depths. The limit of observation enters with a clear boundary. Colour alone cannot reveal the exact emission radius. Motion in the gas also shifts frequency through Doppler effects. Scattering in hot plasma can smear and soften spectral features. Absorption in layered gas can remove specific bands and mimic a redder glow. Finite resolution blends light from many radii into one measured colour. The limit is that redshift must be inferred through models that separate gravity from motion and from plasma effects. The inference is indirect and uncertain near the deepest regions. A small payoff follows from that limit. Even with perfect brightness, measurement gravity and motion can trade roles in the observed shift. The scene returns to the layered disk with a slow drift. The inner layers move faster and stretch bright clumps into arcs. Those arcs send light outward through curved paths. Some paths loop briefly and then depart. Each departing ray carries a frequency reduced by its climb. The combination of bending and redshift produces a calm signature. The darkest center stays dark. A thin ring stays bright. The ring's hue stays subtly shifted. Another payoff lands without strain. The horizon remains unseen, but the approach toward it leaves a gradual change in color and brightness. The change is monotonic and smooth. It strengthens as the origin moves inward. A final visual anchor settles the section. A dim pulse travels along the inner arc and fades. The fading is not only distance, it is the packet arriving stretched in both time and frequency. The transition remains gentle and forward. The next step follows how those stretched packets space out in arrival time, and how steady emission can appear to slow and smear near the edge. A steady rhythm near a black hole can arrive as a slow thinning echo far away. Gravitational time dilation makes signals from deep regions appear stretched and delayed to distant regions. In that region, a thin arc of gas glows close to the dark center. Bright patches form in the arc and fade. Each patch is a brief flare. Each flare releases a short train of waves that climb outward. Light behaves as a carrier of both color and timing. The timing is carried in the spacing between crests and in the spacing between pulses. A small payoff settles early. The same process that shifts color also stretches time between events. The outside does not receive a compact burst. The outside receives a longer and weaker sequence. The primary visual anchor becomes a line of luminous beads along the inner arc. The beads brighten one after another. The pattern is simple near the source. The beads look evenly spaced in time. Closer to the horizon, the spacing between beads grows in the received signal. The growth is smooth and continuous. The physical detail stays clear. The inner arc shows a steep gradient in brightness. The gradient is strongest near the dark boundary. The gas there is thin and hot. It radiates in short flickers rather than steady glow. Those flickers are the pulses that carry time outward. A new term appears once and then returns to ordinary language. Gravitational time dilation is slower, proper time deeper in gravity. Like drips from a stalactite that seem to slow as the water thread lengthens, intervals appear to widen. Like ripples released from a spring that is gently extended, the spacing between markers grows. It matters because the horizon is approached through timing, not through a visible line. The scene narrows to one bright bead. The bead brightens quickly and then dims. A signal would be this change in brightness. It travels outward as light. Far away, the change is not seen as a clean blink. It is seen as a longer, fading pulse. Part of the lengthening comes from time dilation. Part comes from curved paths that add travel time. A small payoff lands softly. Delay is created by both slower clocks and longer routes. One number can hold the idea without strain. A pulse that lasts 1 second locally can appear to last about 10 seconds far away. That factor is like a short sigh becoming a long breath. The example is not a fixed rule. The factor grows as the origin moves inward. Near the horizon, the factor can become very large. The received pulse becomes stretched beyond easy counting. The bead line in the visual anchor now looks like a string pulled taut. The beads are still present. The spacing between them grows in the received pattern. The string does not break. It simply lengthens. A small payoff clarifies what is and is not happening. Nothing is seen to freeze as a physical object. Only the outward news of change is delayed and diluted. The gas continues to move. The inner arc continues to shear. The observer effect is in the signal. The physical detail remains concrete. The inner arc has thin layers that slide past each other. Those layers create narrow streaks that curve around the dark center. Each streak is a track of heated gas. Each track emits light with a local rhythm. The outside receives that rhythm altered. The alteration is the story. The scale shift is gentle and wide. Locally, the difference is between one tick and the next. Far away, the difference becomes the spacing between brightening episodes across a whole scene. A short local time scale becomes a long-distant time scale. A minute near the inner arc can correspond to hours in the received pattern depending on depth. This is not a trick of distance alone. It is the structure of time in curved space-time. A small payoff arrives as a clean statement. The deeper the origin, the slower the received cadence. The primary analogy enters in a quiet natural form. The effect is like seeds carried in a slow stream through a widening marsh. Near the source, seeds pass a point with regular spacing. In the marsh, the flow spreads and slows. The spacing between arriving seeds increases. No seed is lost by choice. The environment changes how the spacing is delivered. Likewise, space-time changes how pulse spacing is delivered outward. The analogy remains a guide and does not replace the physics. The physics stays simple. Time runs differently at different depths. Signals climb out and are stretched in the process. The visual anchor shifts to show the same bead line from farther away. The beads look dimmer now. The dimming is not only distance, it is also the spreading of energy across a longer time. A fixed amount of radiated energy is delivered over a longer interval. The received power per moment decreases. Another payoff settles into place. Stretching time also reduces brightness at the same time. The horizon is approached through a double fading. Pulses spread out. Pulses dim. The limit of observation enters here with a clear boundary. No finite measurement can witness a clean moment of crossing the horizon. The received signal from deeper and deeper regions becomes weaker and slower. It blends into background emission and scattering haze. Finite sensitivity sets a practical flaw. Finite resolution blends light from many radii into one pixel of brightness. Scattering in hot plasma smears sharp timing into a smooth glow. The limit is that the outside cannot discriminate a final tick at the edge. The outside can only infer an approach from how ticks elongate and fade. A small payoff follows from this limitation. The horizon acts like a boundary that hides events by stretching their outward signatures beyond detectability. The scene returns to the inner arc with careful motion. Bright patches migrate along the arc. The migration is driven by shear and by density waves in the gas. The waves are visible as faint ridges. Each ridge compresses gas slightly. Each compression increases emission briefly. These are the beads in the anchor. The outside receives the ridge pattern as a slower undulation. The undulation is not a calm lie. It is a transformed truth. Timing is transformed by depth. Another payoff arrives by separating two kinds of time. Local time for the gas remains ordinary in its own frame. Distant time for received signals stretches. Both descriptions are consistent. They refer to different clocks at different depths. The confusion dissolves when clocks are treated as local. The outside does not own a universal time that all regions share. The visual anchor becomes more abstract and calmer. The beads blur into a soft band. The band still shows a gradient. It is brighter on the side where emission originates higher up. It is dimmer closer to the dark centre. The band also carries subtle ripples. The ripples are the stretched remains of local flickers. A final payoff settles into quiet certainty. Near the horizon, observation is shaped by fading and delay. The boundary is never seen directly in timing. It is seen in the way timing fails to remain sharp. The closing sentences lean gently forward. The next step follows the shape of space-time itself, and how curvature replaces ordinary straightness with a quiet kind of steepness. Curvature is often described as an idea yet near a black hole. It behaves like a quiet terrain that directs every route. Space-time curvature makes the straightest paths bend even when nothing pushes. At this distance, a thin haze of ice grains drifts in a broad halo. The grains glow faintly where a distant starfield lights them. The glow outlines a loose lattice of dim strands. The strands appear almost straight, far from the centre. Closer in, the same strands bow into arcs around the darkness. Light behaves as a traveller that follows available straightness. Near strong gravity, straightness is not the same everywhere. A small payoff settles into place. Bending is not a force acting on light. Bending is the shape of the routes that remain straight in curved space-time. The primary visual anchor holds the lattice steady. Lines of glow curve like long grasses laid down by an unseen contour. The curvature is smooth. No kink or corner appears. The physical detail is a steady gradient. The closer the strands pass to the centre, the tighter their bow. Farther out, the bow relaxes and the lines recover a calmer direction. One safe number anchors the neighbourhood. Within about 10 horizon radii, the bending becomes strong and unavoidable. 10 times a boundary scale is like 10 steps away from a doorway. It is not far in that local sense. It is far in consequence because direction itself is altered. Another payoff arrives with that contrast. Curvature is local, yet its effects accumulate over long travel. A ray that bends by a little at each moment can end far from its starting line. In that region, a bright patch in the disk sends a brief flash. The flash leaves as many rays. Some rays depart directly. Some rays curve, skim the inner region and depart later. The departure pattern is a quiet fingerprint of curvature. A new term appears once and then returns to plain language. A geodesic is the straightest path in curved space-time. Like a stream that follows the lowest channel in a valley, it follows the shape it is given. Like a ribbon drifting in a steady whirl of air, it bends without any tug. It matters because both light and freely moving matter trace these paths. The lattice scene now becomes more instructive. A set of glowing strands seems to form a net. The net is not a material mesh. It is a visual guide for direction. Near the centre, the guidelines converge. Their spacing changes. Their angles change. A small payoff clicks into place. Curvature can be read as a change in how neighbouring straight paths separate or converge. The change is slow at first. It becomes rapid closer in. This is where intuition reaches a gentle limit. Ordinary intuition imagines space as a fixed stage. It imagines time as a separate ticking. Near the black hole, the stage and the ticking are linked. Curvature includes time. That part cannot be pictured as a simple bend in space alone. The limit of intuition is that a three-dimensional picture is incomplete. The best image is a set of rules for paths, not a solid shape. The scene offers a calm workaround. At this distance, the focus stays on what can be traced. Rays and freely drifting grains reveal the rules by their motion. A grain released from rest far away drifts inward. Its track looks almost straight from far out. It becomes more curved as it nears the centre because what counts as straight has changed. Another payoff follows immediately. Falling does not require a pull felt as a shove. Falling is following straightness in a curved geometry. The physical detail becomes more concrete in the disk. The inner edge shows thin layers and sharp brightness boundaries. A narrow bright ridge runs along the disk like a seam. The seam is stretched by shear. It becomes a long arc. Its light outlines the curvature of nearby routes. Rays leaving the seam do not spread evenly. They are focused and defocused by the geometry. A calm scale shift arrives. A small region near the inner edge shapes the appearance of the entire scene far away. A bend that happens over a short local span determines where a ray lands after crossing vast distance. The local and the distant are tied by the path. Another payoff settles into clarity. Curvature is a lens that does not need glass. It is a focusing of routes by geometry alone. The lattice anchor returns in a new light. The glowing strands now seem to compress near the centre. Their spacing shrinks as they pass close. Then their spacing widens again farther out. This change hints at why bright regions can appear magnified or stretched. It also hints at why darkness can appear larger than the horizon. The routes that would have filled the central view are redirected away or captured. The limit of observation enters with a clean boundary. Curvature cannot be measured as a substance. It is inferred from trajectories and from light patterns. Finite resolution blends many nearby paths into one smear. Scattering in hot plasma can soften sharp focusing into haze. Motion in the disk adds additional shifts that can mimic geometric effects. The limit is that curvature must be reconstructed through models, and those models have degeneracies. Several different environments can yield similar brightness arcs. The lattice still gives a stable lesson. Even when details blur, the overall bowing of paths remains. Another payoff arrives by separating local calm from global distortion. In any tiny region, motion looks almost straight. In that tiny region, geometry can be treated as nearly flat. Yet when many tiny regions are stitched together, the stitched result curves, the mind expects one global straightness. The black hole replaces it with a patchwork of local straightness that cannot align. The primary analogy becomes a quiet natural scene. Curvature is like a landscape of gentle ridgelines under shallow snow. Each step can feel level. Over many steps, the route still arcs around unseen contours. Straight walking does not guarantee a straight track on the hillside. Likewise, a geodesic feels straight locally, yet it bends globally in the curved region. The analogy remains calm and grounded. It also respects the deeper point. A path can be straight without being a line in ordinary sense. The visual anchor softens into a final image. The lattice fades as the glow dims. The disk remains as a curved band with layered gradients. The dark center remains still. The routes around it remain shaped. The final payoff settles without urgency. Curvature sets the stage for every other effect near the horizon, from bending to redshift to delay. The next step moves from route shape to route difference. The focus shifts to gradients that stretch and squeeze, and to the tides that appear when curvature changes across nearby points. A black hole does not only bend paths, it also makes nearby paths separate at different rates, and that difference is what tides mean here. In that region, a tidal gradient stretches along the inward direction and squeezes across it. At this distance, a thin filament of dust drifts inward as a pale thread. The thread has two denser knots along its length. The knots glow faintly from distant starlight. A darker lane sits between them where the dust is thicker. Light behaves as a tracer of shape. The filament shows what motion does when gravity changes across small distances. A small payoff settles quickly. Tides are not a new force. Tides are the difference in gravity from one point to a nearby point. The primary visual anchor holds the filament steady as it falls. The inner knot moves inward faster than the outer knot. The thread between them lengthens. It becomes thinner. The outer knot still lags. The inner knot keeps gaining. The physical detail is simple and precise. The filament is being pulled into a longer line. At the same time, the filament narrows sideways. This is the squeeze. Stretching and squeezing happen together. A new term appears once and then returns to plain language. A tidal field is a gradient of gravity across space. Like wind shear in a fog bank, the top layer drifts faster than the bottom. Like a river delta where one channel accelerates, nearby water splits and spread. It matters because objects are not points. Objects have size, and size makes gradients relevant. The scene shifts from dust to gas near the disk. A thin sheet of hot gas wraps around the dark center. The sheet shows layers like faint ripples. In the inner region, the ripples are tighter. The brightness changes over short distances. The inner edge looks sharper and more strained. A small payoff arrives. The same gradient that stretches dust also shapes the thickness of the gas. It can pull material into narrow streams. It can also compress material into denser ridges. The filament anchor returns as a guide. The two knots now appear farther apart. The connecting thread is thinner. It starts to fray at the edges into faint wisps. The wisps peel away along curved paths. Some wisps fall inward sooner. Some lag behind and spiral longer. This creates a layered look. The layer pattern is a physical detail that can be seen in the glow. Another payoff settles in plain language. Tides are strongest where the change in gravity is steepest. That steepness rises rapidly as the distance to the centre decreases. The scale shift is gentle and wide. On a small scale, the thread lengthens by a visible amount. On a larger scale, whole streams in the disk can become long arcs. Over a short local time, a compact clump becomes a streak. Over a longer distant time, the streak becomes a persistent structure that guides where light is emitted. One safe number anchors how quickly the tide can change with position. If the distance to the centre is cut in half, the tidal effect grows by about 8 times. That factor is like doubling a shadow's length and finding it becomes far more than doubled. The payoff is immediate. A small inward drift can produce a large increase in stretching. This explains why the inner disk looks finely structured. It also explains why features can change quickly near the centre. The visual anchor shifts to a new calm image inside the same scene. A narrow ribbon of gas peels off the disk and falls inward. The ribbon twists into a spiral. Its outer edge remains thicker. Its inner edge becomes a thin strand. The twist reveals sideways squeezing. The ribbon narrows as it lengthens. The physical detail is the changing width. It is a moving boundary between thicker and thinner layers. A small payoff follows. Stretching does not only pull apart, it also heats by compression in directions perpendicular to the stretch. Compression increases temperature and brightness in some patches. This is why tides can help create bright knots even while they tear structures apart. The limit of intuition appears here and needs a clear boundary. Ordinary intuition expects pulling to separate and never to compress. Near a black hole, geometry enforces both at once. The same tide that lengthens a line also squeezes its cross-section. The mind wants one simple push or pull. The region provides a coupled pair instead. The best picture is a changing volume. Length increases while width decreases. The volume can change depending on the flow. The scene returns to the filament with 2 knots. The inner knot now looks brighter and more compact. The outer knot looks dimmer and broader. The thread between them is faint. Its edges are ragged. A payoff settles quietly. Tides can turn a connected structure into a set of separated pieces without any collision. The separation is gradual. It follows from acceleration. The next payoff follows from mass and scale without adding new clutter. Larger black holes have weaker tides at their horizons. Smaller black holes have stronger tides near their horizons. This is a scale shift that feels paradoxical at first. The boundary of no return can be gentle in stretching for a very massive black hole. The same boundary can be violent in stretching for a much smaller one. The difference comes from how curvature changes with distance, not from the existence of the horizon itself. The primary analogy remains the fog shear and keeps it calm. In a gentle shear, layers drift apart slowly. In a steep shear, layers tear into filaments quickly. The same fog is present in both. Only the gradient changes. Likewise, the same rule of tides is present in all cases. Only the steepness differs. The limit of observation enters with a practical edge. Tides cannot be measured directly as a force meter reading. They are inferred from shape changes, thickness changes and timing changes in emission. Finite resolution blends thin filaments into a smooth band. Scattering in hot plasma blurs sharp edges into haze. The inner region is also obscured by overlapping paths of light. Many rays loop and arrive from different angles. This mixes information from different depths. The limit is that a filament seen in light does not map to a single physical line. It maps to a family of paths and a model of emission. A small payoff follows from that limit. Observations reveal consistent signatures of stretching, but they cannot isolate a single strand's full history. The horizon remains hidden. The interior remains unreachable by signals. Tides therefore become an outside story told through outside matter. The scene returns to the disk layers again. A thin ridge forms and then elongates. It becomes a bright arc. The arc fades and leaves behind a dimmer streak. The streak continues inward and becomes too faint to follow. This is another payoff. Even without seeing a crossing, the approach can be read in the increasing fragility of structure. The closer the flow passes to the centre, the more fine and thread-like it becomes. The physical details become subtle and calm. Brightness gradients sharpen. Boundaries between layers become narrower. Streams curve more tightly. These are all exterior signs of a steepening gradient. The closing image eases outward for a soft landing. The filament that began as a thick thread is now a faint spray. The two knots are no longer connected by a visible bridge. The disk remains as a broad band around the darkness. Its inner rim shows thin arcs and narrow ridges. The transition stays gentle and forward. The next step follows how these exterior structures shaped by tides and curvature contribute to the wider shadow pattern and the silhouette that appears larger than the hidden boundary. A boundary can hide an interior, yet the outside still carries faint traces of what falls in. The limit of observation near a horizon is that only indirect evidence can be gathered from the exterior environment. At this distance, a thin mist of plasma surrounds the dark centre. The mist is not uniform. It forms layers that drift like translucent curtains. Bright specks appear where the mist compresses. The specks fade and leave behind dim trails. Light behaves as both messenger and sculptor. It reveals the mist. It is also redirected by curvature into arcs and rings. A small payoff settles early. Almost everything that can be observed comes from material outside the horizon, not from the horizon itself. The primary visual anchor forms as a faint ripple pattern in the mist. The ripples are concentric yet slightly distorted. Each ripple is a density wave travelling through the plasma. The wave crests brighten where particles crowd together. The wave troughs dim where the plasma thins. The ripples move inward. They do not bounce back. The physical detail is a clean boundary in brightness. A crest has a sharp front edge. Behind it the glow relaxes into a softer gradient. A new term appears once and then returns to plain language. An accretion flow is gas drifting inward under gravity. Like a slow whirlpool, in a pond, the flow carries patterns inward while the surface remains calm. Like dust carried along a slope sheet of ice, the drift is gentle until it reaches steeper ground. It matters because the flow is the visible medium that records the approach to the horizon. A small payoff follows from this framing. The outside never sees a crossing event directly. The outside sees the flow change as it nears the boundary. One safe number anchors how little time a pattern has once it is close. Near the inner region, a pattern can be carried inward in about a few orbits. That is like a leaf circling a drain only a handful of times before vanishing. The exact count depends on conditions, yet the lesson is stable. Close patterns do not linger long, they are short-lived signatures. The ripples in the visual anchor now tighten into smaller spacing near the centre. The spacing change is a physical detail tied to gradient and shear. The inner plasma moves faster. It stretches ripples into arcs. It thins some crests. It thickens others. Light from those crests is also bent. A small payoff settles. The same environment that emits the signal also distorts it. Observation is therefore a combined story of physics and viewing geometry. The scale shift arrives quietly. Locally, a ripple is a small compression of gas. It is a change in density over a modest distance. Far away, that ripple becomes part of a global brightness pattern. The global pattern can look like a ring with uneven thickness. The ring can look like a crescent. It can look like a soft band with a dark centre. A local wave becomes a distant silhouette. Another payoff lands, without emphasis. What is called a black hole image is mostly an image of glowing plasma shaped by space-time. The black hole itself remains unseen. The shadow is a deficit of rays, not a surface. The horizon is deeper still and its location is inferred. The primary analogy enters with a gentle everyday scene. The horizon is like the edge of a thick fog bank at night. The interior cannot be seen. Only the glow of nearby mist is visible. The shape of that glow can suggest where the fog thickens, but it cannot reveal the far interior. The analogy stays calm and it matches the physical limits. The glow comes from the medium outside. The interior remains hidden by the rules of propagation. The limit of observation now becomes explicit and specific. Several different arrangements of plasma density can produce similar brightness rings. Several different temperature gradients can mimic one another after scattering. Scattering is a physical detail that matters here. Photons can bounce off charged particles and change direction. This blurs sharp structures. It reduces contrast. It can also delay photons and smear timing signals. Finite resolution adds another limit. Fine ripples smaller than the resolution element blend into smooth light. A third limit is degeneracy between motion and gravity. Doppler shifts from rotating plasma can resemble gravitational shifts. Without perfect separation, models must be used. The limit is that inference depends on assumptions about plasma physics. A small payoff follows. The boundary is not measured by direct touch. It is constrained by consistent patterns across many observations. The ripples in the visual anchor now fade into a broader swirl. A bright arc forms on one side where the plasma is denser or hotter. A dim arc forms on the opposite side. The arc thickness varies. The thickness is a physical detail tied to optical depth, which is how opaque the plasma is. When opacity is high, light escapes from higher layers. When opacity is low, light escapes from deeper layers. This changes what depth is being sampled. Another payoff settles. Observation is not a direct map of radius. It is a map of where photons last interact with plasma. That last interaction surface can sit above the horizon by a changing amount. It can shift with density and with frequency. The scale shift continues in a calm way. A small change in plasma density can move the effective emission layer outward. That local change can alter the apparent size of the dark center in the distant pattern. The black hole can appear to have a larger or smaller shadow depending on how the plasma glows. The shadow is not a fixed outline on the sky. It is a combination of geometry and emission. A small payoff clarifies what remains fixed. The event horizon is fixed by mass and spin. The shadow is more robust than the plasma details, yet it is still measured through those details. The horizon remains the deepest boundary. The outside only sees its influence. The analogy returns with the fog bank. The exact brightness at the edge depends on how thick the mist is and how it scatters light. Yet the fact that the interior cannot be seen remains. The boundary of visibility is a rule, not a choice. The visual anchor now shifts to a calm sequence of pulses travelling through the swirl. A pulse begins as a sharp brightening in one crest. It becomes a smeared glow as it moves inward, and a scattering spreads it. It becomes weaker as redshift and time dilation stretch it. Another payoff lands. Several mechanisms act together to hide deepened vents. Escape angles shrink. Frequencies drop. Time intervals stretch, scattering blurs. Each mechanism alone would soften information. Together they produce a strong veil. The limit of intuition appears again with a gentle boundary. The mind expects a hidden thing to still cast a clear edge. Near a horizon, the edge is softened by the medium. The clearest edge belongs to the geometry of paths, not to a physical wall. Even that geometric edge is inferred through the plasma. The outside must accept a calm uncertainty. It is not ignorance by lack of effort. It is a structural limit. The closing image eases outward. The ripple pattern becomes wider and less distorted. The arcs relax into gentler curves. The dark center remains. The glow remains outside it. The transition stays soft and forward. The next step follows how the shadow itself forms as a silhouette of missing rays, and why that silhouette is larger than the hidden boundary that defines the black hole. A black hole can cast a shadow without emitting any light at all. The shadow is the set of directions from which light fails to reach the outside, Because paths are bent inward. At this distance, the glow around the dark center becomes organized into a calm geometry. A broad band of plasma forms a loose ring. The ring is brighter on one side. It is dimmer on the other. Between the bright band and the dark center, a clean deficit appears. The deficit looks like a circular bite taken out of the scene. Light behaves as trajectories that can be captured or redirected. When many trajectories are removed, a shadow appears as missing brightness. A small payoff settles early. The shadow is larger than the event horizon, because many rays are trapped without starting at the horizon. The primary visual anchor is a steady silhouette in a field of curved arcs. A lattice of faint background starlight passes through the region. Some lines arc around the center and continue. Some lines terminate into the darkness. The termination is not absorption by a surface, it is capture by geometry. The physical detail is a sharp brightness boundary at the inner edge of the glow. The boundary is not perfectly sharp. It is softened by scattering and by finite resolution. Yet a clear transition remains between glowing ring and dark deficit. One safe number anchors the scale of that deficit. The apparent shadow radius is about 2.5 times the horizon radius. That factor is like turning a small coin into a larger coin by adding a wide rim. The horizon stays hidden inside. The visible deficit comes from a wider region of missing paths. A small payoff lands with that number. The shadow is a map of unstable light paths near the photon sphere, not a picture of the horizon itself. A new term appears once and then returns to plain language. The black hole's shadow is the silhouette of captured light directions. Like a hollow in a fog-lit field where lamps cannot illuminate it is a gap defined by missing rays. Like a drain pattern on wet sand where water lines disappear into a sink, it is a deficit defined by removed trajectories. It matters because it turns invisible geometry into a visible outline. The scene slows to the bright ring itself. The ring has thickness. It has a gradient from inner rim to outer rim. The inner rim is brighter because many rays linger and wrap around before escaping. The outer rim is softer because rays there depart more directly. The physical detail is a layered rim. It resembles a thin band of glowing smoke with a sharper inner edge. A small payoff settles. The bright ring is enhanced by rays that nearly orbit and then leave, which increases the brightness around the silhouette. The shadow is framed by delayed light. The scale shift is calm and precise. Locally, a ray that passes slightly closer than a critical distance is captured. A ray that passes slightly farther is deflected and escapes. That local difference is tiny in angle. Far away, it becomes a macroscopic difference in whether a direction on the sky is bright or dark. A small change in aim becomes an entire missing region in the image. Another payoff arrives without some strain. The shadow is a threshold phenomenon. It is the boundary between directions that connect to the outside and directions that do not. The primary analogy enters as a quiet, everyday scene. The shadow is like a circular patch of calm water inside a field of ripples. Ripples approaching the patch are refracted into a swirl and never cross it cleanly. The patch stays smooth because waves that would fill it are redirected away. The patch is not a wall. It is the result of how paths curve in that region. The analogy stays gentle and does not replace the physics. It helps hold the idea of a deficit created by root bending. The visual anchor deepens with arcs that wrap around the deficit. A bright streak in the plasma emits light. Some of that light goes outward and leaves quickly. Some passes near the turning region and wraps around to the far side. This creates a secondary glow on the opposite side of the ring. The ring therefore can appear asymmetric even when the underlying plasma is simple. A small payoff settles. The shadow edge can look sharper on the side where more wrapped light accumulates. It can look softer where scattering dominates. The limit of observation enters with a clear boundary. The shadow outline is not drawn directly by a compass. It is reconstructed from brightness patterns in a turbulent plasma. Finite resolution blurs the inner rim. Scattering in hot plasma spreads light across the boundary and fills part of the deficit. Emission can vary with time, which changes contrast and edge sharpness. Doppler effects from rotating plasma can brighten one side and dim the other. The limit is that the exact shadow size depends on modelling of emission and scattering. The size is robust in a broad sense, yet not exact in every snapshot. A small payoff follows from this limit. The most stable feature is the existence of a central deficit with a bright rim, not the exact pixel edge of the deficit. The scene shifts to a calmer moment. The plasma ring becomes smoother. The bright side remains brighter. The dim side remains dimmer. The central deficit remains. The arcs of background light remain bowed. The visual anchor now shows a gentle wavering of the rim thickness. The rim is thin where the plasma is optically thin. It is thicker where scattering layers are present. The physical detail is the changing rim width. This detail ties the shadow to the environment. A small payoff settles. The black hole geometry sets the possible silhouette. The plasma sets how clearly the silhouette is painted. Another payoff arrives by separating shadow from darkness in the disk. A dark lane in the disk can be produced by low density. The shadow is a deficit of reachable directions even if plasma exists there. These are different kinds of darkness. One is emissive, one is geometric. The shadow remains when emission changes as long as some light exists around it. The scale shift widens again. A silhouette only a few horizon radii wide can be used to infer the presence of a black hole across vast distances. A compact geometry becomes a distant signature. The mind expects that distance erases detail. Here, distance preserves a simple shape because the shape is defined by stable geometry. The closing image softens into quiet certainty. The central deficit remains round and steady. The rim remains a glowing band with layered gradients. The background arcs remain gently bent. The transition stays soft and forward. The next step follows what changes when the black hole spins and how rotation reshapes the silhouette and the surrounding flow without letting the horizon open. Rotation can be invisible, yet it can still twist the routes that light and matter must follow. A spinning black hole drags space-time nearby, tilting paths and shifting the balance of what can escape. At this distance, the glowing ring around the dark center is no longer evenly arranged. One side of the ring looks sharper and brighter. The opposite side looks softer and dimmer. The inner rim also looks slightly displaced, as if the silhouette is nudged off-center. Light behaves as trajectories that inherit the twist of the surrounding geometry. The twist is not a wind. It is a change in which directions count as straight. A small payoff settles early. Spin does not open the horizon. Spin reshapes the neighborhood outside it, changing the pattern of bending and brightness. The primary visual anchor is a slow-turning spiral of thin plasma sheets. The sheets are layered like ribbons in clear water. They wrap around the dark center with uneven spacing. On one side, the layers are packed closer. On the other side, they are stretched farther apart. The physical detail is a shear pattern. The shear is stronger where the flow is forced into faster motion by the twist. A new term appears once and then returns to ordinary words. Frame dragging is the twisting of space-time by rotation. Like a thick syrup stirred from below, nearby layers are carried into a shared swirl. Like leaves in a slowly spinning eddy paths curve, even when nothing touches them. It matters because it changes which way a ray can go and still escape. The scene tightens to the inner rim of the disk. A bright arc forms where the plasma is hottest or densest. The arc is not symmetric. It leans forward in the direction of rotation. The opposite side is fainter and more diffuse. A small payoff lands quietly. Rotation makes one side look favoured because rays from that side gain easier outward routes. Rays from the opposite side face a steeper climb in direction space. One safe number anchors the scale of the effect without strain. In strong spin, the innermost stable orbit for matter can sit about half as far in as in the non-spinning case. That change is like moving from the outer edge of a pond to near the centre, without changing the pond surface. It is a shift in where stable motion is possible. It brings glowing material closer to the horizon on the favoured side. The physical detail follows. The inner edge of emission becomes thinner and more tightly curved. It forms a sharper crescent. That crescent hugs the dark deficit more closely on one side. On the other side, the emission edge sits farther out and looks broader. A small payoff settles. Spin can change how close bright plasma can orbit without plunging, which changes how compact the bright rim appears. The scale shift remains calm. Locally, the twist is a slight change in the direction a freely moving particle naturally takes. Far away, that slight change reshapes the entire silhouette and the distribution of brightness around it. A small local bias becomes a large global asymmetry. Another payoff arrives. The shadow remains central and stable in its existence, yet its outline can become slightly distorted and shifted by spin. The primary analogy enters as a gentle, everyday scene. The region is like a slowly turning carousel covered with thin mist. On the carousel, a drifting ribbon tends to curve with the rotation. A ribbon released in the direction of rotation glides farther before it sags inward. A ribbon released against the rotation folds inward sooner. The carousel is not a force field. It is the moving platform that changes how paths look from above. Likewise, frame dragging is a moving geometry that changes which routes remain outward. The analogy stays quiet and grounded. The visual anchor returns to the layered plasma ribbons. A narrow, bright filament forms and then stretches. It becomes a thin arc. The arc wraps around and sends a faint secondary glow to the far side through bent paths. The secondary glow is uneven. It appears in a different place than in the non-spinning case. A small payoff lands. Spin changes, which bent paths linger, and which depart quickly so the ring can look thicker on one side and thinner on the other. The limit of observation enters with a clear boundary. Asymmetry in brightness does not uniquely prove spin. Uneven plasma density can mimic the same crescent. Temperature gradients can mimic it too. Scattering can blur one side more than the other if opacity varies. Finite resolution can also turn a complex ring into a simple crescent. The limit is that spin must be inferred through models that separate geometry from emission physics. The inference is indirect. It relies on consistent patterns across time and frequency, not on one snapshot. A small payoff follows from that limit. Spin leaves a signature in how stable orbits shift and how path bending becomes direction dependent, but that signature is filtered through plasma. The scene shifts to timing and direction without adding new clutter. A brief pulse in the inner rim sends rays outward. Rays leaving along the favoured direction depart with less delay. Rays leaving against the favoured direction can loop longer or fall inward more easily. This produces a subtle skew in arrival times and brightness around the ring. Another payoff settles. Spin can bias not only where light appears, but also how quickly changes propagate to distant regions in different directions. The physical detail becomes the rim itself. The rim has a sharper inner edge where rays linger near the turning region. It has a softer outer edge where rays depart more directly. Under spin, the sharp edge is more pronounced on one side. The soft edge broadens on the other. The silhouette therefore looks like a shifted shadow with a bright crescent. The scale shift widens again in a gentle way. A small change in the innermost orbit radius changes the entire energy release region. That alters the overall colour and timing of emission. Over long distances, the effect becomes a persistent difference in the received pattern. The region near the horizon remains unreachable by direct signals from inside, yet the near outside becomes a stronger sculptor of what is seen. The closing image eases outward. The crescent remains, the dark deficit remains, the layered ribbons remain in slow rotation, the transition stays soft and forward. The next step follows the region where rotation becomes unavoidable for all motion, and the zone where stillness stops being an option, even outside the horizon. Some regions outside a spinning black hole feel calm in space, yet still cannot remain still in time. The ergosphere is a zone where rotation drags space-time so strongly that no stationary path exists. In that region, the inner glow takes on a subtle tilt. The bright crescent leans forward and wraps closer to the dark deficit. The dim side looks more washed. A thin veil of plasma forms a shell above the disk. The shell is patchy. It has translucent layers with ragged edges. Light behaves as curved routes through a moving geometry. Routes that would be symmetric in a quiet space-time become biased in a rotating one. A small payoff settles early. The ergosphere is not the horizon. It is an exterior zone where motion is unavoidable because space-time itself is moving. The primary visual anchor is a glassy bubble of faint glow around the dark center. The bubble is not perfectly spherical. It is slightly squashed and twisted. Within the bubble, drifting strands never hang in place. Every strand slides around in the same overall direction. The physical detail is a shared drift. Even wisps that start with no sideways motion develop it. The drift becomes stronger closer to the center. A new term appears once and then returns to plain language. The ergosphere is the region where space-time rotation forces co-motion. Like leaves on a broad, slow whirlpool, every leaf must circulate even if it tries to pause. Like a gentle conveyor of air inside a rotating room, dust cannot remain fixed to one spot. It matters because it shows where rotation becomes a rule of the environment. The scene tightens to the boundary of the bubble. The boundary is not a sharp wall. It is a gradual change in behavior. Outside it, a path can be arranged to hover in place relative to distant stars. Inside it, hovering fails. Any object would be carried around. A small payoff lands softly. The boundary is defined by what counts as a possible trajectory, not by a visible surface. The physical detail remains visible through plasma motion. Thin sheets curve around and shear. Their edges fray into threads. The threads all share a sideways drift. This drift is a signature that the environment is dragging frames. One safe number anchors a sense of extent without strain. For a very rapidly spinning black hole, the ergosphere can reach out to about twice the horizon radius near the equator. Twice a boundary scale is like stepping from a doorway to the next room. It is close in local distance. It is large in consequence because it changes what stillness means. A small payoff follows. Inside that zone, even light paths are biased. Escaping rays are more likely in the forward direction than the backward direction. The bright crescent becomes more natural as a result. The scale shift is calm. Locally, the change is a slight twist in which direction is easiest. Far away, the change is a whole asymmetry in brightness distribution around the shadow. The geometry reshapes a global picture through local constraints on trajectories. The visual anchor shifts within the bubble. A faint ribbon of plasma rises above the disk. It lifts into the shell and then spirals. The ribbon's inner edge is thinner. Its outer edge is thicker. The thickness gradient shows compression and shear. As it spirals, it wraps around the dark center more than once. The wrap is not a stable orbit. It is a forced drift. Another payoff lands. The ergosphere makes angular motion available as a kind of shared current. Material can exchange energy with that current through interactions, yet the interior remains hidden. The horizon remains a one-way boundary for signals. The shell is still outside and visible. The primary analogy remains the whirlpool and keeps it gentle. A leaf can circle faster near the center because the water rotates faster. It cannot stay fixed even if it is light. The water here is space-time geometry. The motion is not friction. It is the shape of allowed paths. The limit of intuition appears and needs a clean boundary. Ordinary intuition imagines a region of space that can rotate like a solid. Space-time rotation is not like a rigid disk. It is not an object spinning in a background. It is the background itself that changes what paths are. This cannot be pictured as gears or a wheel without losing accuracy. The better image is a rule that forbids rest in a region. The region is defined by the impossibility of a stationary world line. That rule is subtle, and it remains external to the horizon. The limit of observation arrives next with a practical edge. The ergosphere boundary is not traced directly by a line of light. It is inferred from plasma behavior and from asymmetries in emission. Plasma turbulence can imitate shared drift. Magnetic stresses in the flow can also create spirals and bias. Scattering can blur the shell and hide fine edges. Finite resolution blends the shell with the inner disk. The limit is that the ergosphere is diagnosed through consistency, not through a single crisp boundary in an image. A small payoff follows from that limit. Even without a sharp edge, the idea of unavoidable motion explains why certain asymmetries persist. It also explains why the inner flow can appear locked into a preferred direction. The scene returns to the bright crescent and the shadow. The crescent now looks slightly displaced relative to the centre of the deficit. The deficit remains the shadow. The displacement is caused by direction-dependent bending and emission. The physical detail is the inner rim thickness. It is thinner on the forward side, it is thicker on the backward side. A small payoff settles. Rotation can shift where the brightest ring forms, even though the shadow remains the central missing set of rays. The scale shift widens once more. A region only a few horizon radii across imposes a global handedness on what is seen. That handedness is stable over long times, even as local plasma flickers. Over seconds in local time knots form and dissolve. Over long distant time, the favoured direction remains. Another payoff lands softly. The ergosphere is a checkpoint where geometry becomes dynamic in a way that can be inferred from persistent bias. The closing image eases outward. The bubble shell becomes fainter and more diffuse. The disk remains as a band with layered gradients. The shadow remains as a calm deficit. The transition stays soft and forward. The next step follows how energy and rotation can be redistributed in the surrounding plasma, and how steady patterns can emerge from a region where motion cannot stop. A steady pattern can rise from chaos when the flow is forced to share one direction and one rhythm. Outside, a black hole-ordered structures emerge because rotation curvature and magnetic tension guide plasma into channels. At this distance, the glowing ring is joined by faint, elongated arcs that extend above and below the disk plane. The arcs are not straight. They curve gently and fade into darkness. The disk itself shows narrow bright lanes that persist longer than nearby flickers. Light behaves as a reporter of where plasma is denser, hotter, or better aligned for emission. The patterns that remain are the ones the environment keeps rebuilding. A small payoff settles early. Order near a black hole often means a structure that is constantly renewed, not a structure that stays still. The primary visual anchor is a braided set of luminous strands rising from the inner disk. The braid has 3 distinct strands. Each strand is thin and slightly translucent. The strands twist around a central dark gap like a slow helix. The physical detail is a layered thickness. Each strand has a bright spine and a dimmer sheath. The spine is sharper. The sheath is softer and more diffuse. A new term appears once and then returns to ordinary language. Magnetic field lines are directions that guide charged particles. Like stretched rubber bands in a bowl of water, they pull and align nearby motion. Like threads in a piece of cloth, they set preferred directions for tension and flow. It matters because magnetic tension can organize plasma into long, coherent strands. The scene stays calm and close to the braid. A bright knot forms on one strand. It travels along the strand and fades. A second knot forms behind it and follows. The knot spacing is not regular, yet the path is. The strand remains where it is because the field keeps it shaped. A small payoff settles. Motion can be turbulent, but channels can still be stable when guided by tension. The disk below shows a boundary where a bright lane meets a darker lane. The boundary is sharp for a short distance. It then becomes ragged and breaks into smaller filaments. This is a physical detail of shear and layering. A second payoff lands. Shear breaks features apart while magnetic tension can stitch some of them into longer arcs. One safe number anchors a timescale without strain. A coherent strand can persist for about 10 orbital periods before it is reshaped. 10 cycles is like a slow pendulum repeating a familiar swing before a draft changes it. The exact count varies, yet the point is stable. These are not permanent beams. They are recurrent patterns. The scale shift is gentle. A knot travelling along a strand is a local event. The collective presence of many knots creates a global glow that frames the shadow. Local bursts become a stable-looking outline when averaged over time and over many strands. Another payoff arrives. The image of a black hole is often an average of many brief reorganizations into similar shapes. The braid anchor lifts slightly higher above the disk. The strands widen and then narrow. The bright spines become more pronounced near the base where the disk feeds them. The sheath becomes more visible farther out where the plasma thins and scatters less. The physical detail is a gradient in opacity. Near the disk, the sheath is thicker and more glowing. Farther out, the sheath becomes faint and the spine dominates. A small payoff settles. The same strand can look different at different heights because the emitting layer changes. The primary analogy enters in a gentle, everyday form. The strands are like thin steam trails above warm water at dawn. The steam is never the same parcel of air, yet the same lanes of rising steam appear again and again because the water surface keeps supplying heat in the same places. The analogy stays calm and accurate in spirit. The structure is maintained by conditions, not by persistence of the same matter. The limit of observation enters with a clear boundary. Magnetic structure cannot be seen directly. Only emission and motion can be seen. Different magnetic configurations can produce similar brightness braids. Different particle energies can also mimic the same spines and sheaths. Scattering can blur strand boundaries and make one braid look like two. Finite resolution blends neighbouring strands into a single arc. The limit is that field geometry is inferred from models not traced as a visible line. A small payoff follows. Even without a direct view of fields, the existence of long-aligned strands suggests tension and guiding forces in the plasma. The scene returns to the disk lanes. A bright lane splits into two. The split persists for a short distance. Then one branch fades while the other strengthens. The physical detail is a forked ridge in brightness. The fork shows how flow can distribute and then choose a dominant channel. Another payoff lands. Channel selection can happen through feedback. A slightly denser lane emits more. That emission cools or heats regions differently. That changes pressure and flow. The result can reinforce one path. This is a soft explanation that stays within observation. The scale shift continues. A fork that is small compared to the disk radius can still influence the overall brightness asymmetry around the shadow. It can also influence how often knots form on the rising strands. Local channeling becomes a global pattern. The braided anchor now shows a slow wobble. The strands drift as a group. They remain braided, yet the braid axis tilts slightly. The tilt is subtle. It is another physical detail of a changing flow. A small payoff settles. Stability here means repeatable form, not fixed position. The braid remains a braid even as it shifts. The analogy of steam lanes holds. The lanes drift with changing air, yet the pattern returns. The closing image eases outward. The bright crescent remains around the shadow. The braided strands remain faint above and below. The entire scene feels organized without being rigid. The transition stays soft and forward. The next step follows how these recurring patterns evolve over long times, and how a black hole can change its surroundings across scales from moments to eons. A steady silhouette can persist while everything around it changes at many speeds. The long-term behavior near a black hole is a cycle of supply and flow. It brightens or dims the surrounding glow without altering the hidden boundary. At this distance, the bright crescent sometimes thickens into a fuller ring. Sometimes it thins into a narrow arc. The dark deficit stays calm at the centre. A faint haze above the disk appears and then fades. Light behaves as a record of where hot plasma is thickest and where the bending of paths concentrates it. A small payoff settles early. The horizon stays hidden in every state. Most visible change comes from the layers just outside it. The primary visual anchor opens in the outer flow as a wide spiral ripple. The ripple is faint and broad. It curls inward like slow bands in a field of wind-made sand. Each band has a brighter crest and a dimmer trough. The troughs look smoother and cooler. The crests look sharper and slightly warmer. The crests drift inward and stretch into long arcs. Between crest and trough, a thin seam marks a change in density. A translucent veil floats above the main layer and softens the pattern. A small payoff lands. Even far from the centre, gentle structure can steer what later becomes the inner glow. A new term appears once and then returns to plain language. Accretion rate is the inward flow of mass per unit time. Like a river that runs clear in one season and heavy in the next, the inflow can be light or loaded. Like runoff after distant rain supply can rise and then relax without changing the riverbed. It matters because the inflow sets how much energy is released as heat before light escapes. A small payoff follows. When the inflow rises, the emitting layer grows thicker and the ring tends to brighten. When the inflow falls, the glow thins and more of the dark deficit stands out. The scene tightens toward the inner rim where emission is strongest. The rim is not a hard edge. It is a region where the flow becomes hotter and the gradient steepens. Brightness rises quickly across a short distance and then relaxes into a softer slope. Small bright knots appear along the rim and slide with the rotation. They dissolve into streaks and then reform. The physical detail is a sharp inner boundary paired with a blurred outer skirt. A small payoff settles. A sharper boundary makes the shadow edge look cleaner. A softer skirt can partly fill the deficit through scattering and repeated bending. One safe number anchors the long view. An outer spiral pattern can persist for about 1 million years before it is erased or rebuilt. 1 million years is like a glacier advancing a small distance across a quiet plain. It is long compared with inner cycles. It is brief compared with the life of a galaxy. A small payoff lands. Feeding can arrive in episodes that last long enough to shape the flow, yet short enough to repeat many times. The visual anchor returns as the spiral crest divides into 2 ribbons. One ribbon fades, the other sharpens into a brighter lane and drifts inward. Its outer edge frays into threads while its inner edge stays crisp for a time. The lane crosses a darker patch and becomes briefly thinner. It then regains its brightness as the density rises again. The physical detail is a moving boundary of opacity. Where the flow is thicker, light escapes from higher layers. Where the flow is thinner, light escapes from deeper layers. A small payoff settles. A change in thickness changes, which layer becomes the visible surface. A second term appears once and then returns to ordinary words. Optical depth is how easily light passes through a medium. Like deep water that turns from clear to dark with depth, the same source can look sharp or muted. Like a thin sheet of ice that becomes milky when layered, transparency can change without changing shape. It matters because a thicker layer hides its own interior and reshapes the apparent ring. A small payoff follows. In a thick state, the ring can look broader, and the shadow edge can look softer even when capture geometry is unchanged. The limit of observation arrives with a clear boundary. Brightness alone cannot reveal the accretion rate with certainty. Relativistic boosting can brighten one side without more mass. Scattering can smear light and blur the inner boundary. Absorption in cooler layers can dim the whole scene and mimic a low state. Finite resolution blends narrow lanes into smooth bands. The limit is that different conditions can produce similar images. A small payoff follows from that limit. Reliable inference comes from patterns that hold across time and across wavelengths, not from a single snapshot. The scale shift widens in a calm way. Near the horizon, changes unfold over only a few orbits. Farther out, supply varies over far longer spans. The inner region responds quickly. The outer region changes slowly. The result is a layered memory in the light. Short flickers ride on top of long swells. A small payoff lands. The same system can look restless in a moment and stable in its long-averaged form. The scene lifts toward the polar regions where density is lower. Faint channels appear where plasma is more ordered. Some energy leaves along these channels as a dilute stream. The stream strengthens when the inner flow is organized and thickens near the base. It weakens when the flow becomes patchier and more opaque. The physical detail is a tapered funnel that is darker near its axis and brighter along its sheath. A small payoff settles. Large-scale influence can begin as a subtle change in how the inner layers arrange themselves. The closing image eases outward to the wide spiral again. The spiral becomes smoother and fainter. The bright crescent remains around the calm deficit. The haze above the disk thins until it is almost invisible. The transition stays soft and forward. The next step follows how these slow cycles of supply and release affect a much larger neighborhood over vast distances and times. A black hole can be silent at its boundary yet loud in its reach across far space. The influence comes not from signals from inside, but from how surrounding plasma releases energy and redirects it outward. At this distance, the bright inner crescent is only the core of a much larger glow. Fainter streams spread into a wide, diluted halo. Long arcs of emission extend away from the disk plane. They are thin and tapered. Their edges are soft and feathery. Light behaves as a tracer of where energy is carried and where density allows it to radiate. A small payoff settles early. The horizon hides information. The environment outside can still reshape vast regions through energy flow and pressure. The primary visual anchor is a broad cone of faint luminosity rising from the inner region. The cone is not sharp, it is a gradual funnel of dim glow. Its center is darker than its sheath. The sheath is brighter along a curved rim. The rim shows a thin, bright boundary where density is slightly higher. Inside the cone, wisps drift outward and then disperse. The physical detail is a layered boundary. The boundary separates a more ordered stream from a surrounding turbulent haze. A new term appears once and then returns to plain language. Outflow is matter and energy moving away from the center. Like fog rolling out of a valley, it can be thin but far-reaching. Like ripples spreading from a dropped pebble, it carries disturbance outward without carrying the pebble. It matters because outflows change what surrounds the black hole, even though the horizon stays hidden. A small payoff lands. The ring and shadow show local geometry. The outflow shows how local release becomes a distant effect. The scene stays calm within the cone. A faint knot forms in the sheath. It drifts outward along the curved rim. It stretches into a long streak and fades. Another knot follows a similar path. The repeated paths suggest a guiding structure. The guiding structure is not a rigid pipe. It is a region where pressure gradients and magnetic tension favor outward motion. The physical detail becomes the cone rim thickness. The rim is thinner near the base. It thickens slightly farther out as surrounding material mixes in. A small payoff settles. Even a dilute stream can gain visibility where it entrains more material and becomes a better radiator. One safe number anchors the scale. The outflow can extend for about 1,000 light years in some systems. 1,000 light years is like a single page in a very long book of galactic size. It is still far enough to cross large neighborhoods of gas. A small payoff follows. An influence that begins within a few horizon radii can reach distances where the central ring is a point of light. The scale shift is gentle. Close in the disk lanes and braided strands evolve over short cycles. Far out, the outflow shapes clouds over long sands. A brief change near the center can become a slow wave in the surrounding medium. The visual anchor widens to include the halo around the cone. The halo is mottled. It has faint layers that look like smoke rings stretched into arcs. Some arcs curve back toward the disk plane and fade. Others continue outward and dissolve into the background. The physical detail is a gradient in brightness that declines smoothly with distance. The decline is not uniform. It has gentle bumps where density rises. Another payoff lands. Distant bumps in brightness mark places where the outflow meets denser gas and converts motion into heat and light. The primary analogy enters as a quiet, everyday scene. The outflow resembles a slow fountain in still air. The water itself is not visible here, only a mist that catches light along the fountain edge. The fountain does not need to be violent to be effective. It slowly moistens a wide area. In the same way a dilute stream can quietly change the temperature and density of large regions, the limit of intuition arrives with a clear boundary. It is tempting to imagine a fixed jet that always points the same way. Real outflows can wobble, fan, or fragment. The cone can shift its axis slowly. The sheath can brighten in patches and then dim. The structure is guided by conditions not guaranteed by a single stable pipe. This makes long-term prediction hard. A small payoff follows. Even without perfect stability, repeated outward channels still transport energy outward over long times. The limit of observation arrives next with practical detail. A faint cone can be confused with scattered light from a thick disk. It can also be confused with a broader halo of hot plasma. Projection effects can turn a wide structure into a narrow one. Finite resolution can blend sheath and core and hide the darker center. The limit is that geometry of outflow is inferred from brightness patterns and motion signatures not seen as a solid boundary. A small payoff follows from that limit. Consistent tapered shapes and repeated knots along a rim support the idea of guided outward flow. The scene returns to the inner ring and then steps outward in calm stages. The bright crescent near the shadow is compact. The cone is larger and dimmer. The halo's larger still and fainter. Each layer is a quieter echo of the inner activity. The physical detail is a nested set of gradients, sharp near the center, soft farther out. A small payoff settles. This nesting explains how a single system can be studied at many scales without ever seeing the horizon directly. The scale shift widens once more into time. Over short times the ring flickers and the cone rim knots drift. Over long times the outflow can alter the density of surrounding gas and change how future inflow occurs. The system forms a slow feedback loop. It is not a signal from the horizon. It is a response of matter outside it. Another payoff lands softly. Even when the inner boundary hides information, the outer environment still carries the long-term imprint of energy release. The closing image eases outward until the cone and halo fade into a gentle darkness. The inner crescent remains as a small concentrated glow. The shadow remains as a calm deficit. The transition stays soft and forward. The next step returns to the limits of observation itself and how the whole arc of inference can settle into a quiet, stable perspective. The nearest edge around a black hole is also the hardest edge to witness. The event horizon never appears as a surface in light. Its presence is inferred from what light can do and what light cannot do. At this distance, the scene settles into three quiet signatures. A dark deficit persists at the center. A bent halo of emission curves around it. A slow pattern of delays and fading marks the last messages that escape. A small payoff arrives early. The horizon is not a visible rim. It is a boundary in the paths that information can take. The primary visual anchor forms as a pale, almost continuous halo that seems to hover around the deficit. The halo is not uniform. It has a brighter arc on one side and a softer wash on the other. Along the brighter arc, tiny beads appear as brief knots. They slide and stretch into threads. They fade before completing a full circuit. The physical detail is a sharp brightness gradient at the inner edge. The edge is steep for a short span. It then relaxes into a broader glow. Light behaves as a map of where many curved paths overlap. Where paths bunch together, brightness rays. Where paths diverge, brightness thins. A small payoff follows. The shadow does not mark the horizon itself. It marks a region where escaping paths are rare. A term arrives once and then returns to plain language. The event horizon is a one-way boundary for light and matter. Like a line of wet sand that only shifts inward with the tide, it is crossed in one direction only. Like dye that can spread outward in a pond but cannot be pulled back into the bottle, information does not return once it passes. It matters because everything that can be known must be carried by the outside flow. A small payoff lands. The outside can reveal how close the boundary is. The outside cannot reveal what lies beyond it. The scene drifts closer to the luminous halo. The brighter arc looks thinner now. It has a crisp inner contour and a slightly frayed outer contour. The fray is a faint haze of scattered light. The haze softens the contrast between halo and deficit. In a calmer moment, the halo looks more complete. In a more variable moment, it breaks into short segments. Each segment brightens and dims like a slow pulse. The physical detail becomes a layered thickness. A thin, bright layer sits on top of a broader, dim layer. A small payoff settles. Two layers can exist because light escapes from different depths depending on opacity and heat. Another term enters once and then returns to ordinary words. Gravitational redshift is light losing energy while climbing out of gravity. Like a ripple that spreads and becomes lower as it covers a wider pond, a signal can weaken as it escapes. Like a stretched spring that relaxes and loses tension, the light shifts to lower energy and becomes harder to detect. It matters because the closest signals can fade into the background without ever stopping. A small payoff follows. Near the boundary, fading can mimic silence. The boundary remains active in gravity, even when the light grows dim. The scale shift becomes gentle and broad. Close-in changes in brightness can occur over short orbital cycles. Far out, the same system can keep its overall geometry for very long spans. The dark deficit stays centered. The halo keeps roughly the same size and shape. The details on the halo drift and dissolve. The outer haze slowly breathes in and out. A small payoff lands. Stability and geometry can coexist with motion and texture. The boundary is fixed in a geometric sense. The surrounding flow is never fixed in detail. The analogy changes to a quiet natural pattern. The halo resembles a dewring on a broad leaf at dawn. The leaf stays in place, the dew beads gather along a faint ridge. The beads slide and merge, some evaporate. The ridge remains as a guide even when beads vanish. In the same way, curved paths guide brightness even when emitting knots change. A small payoff follows. The ring-like structure is not a rigid object, it is a preferred set of paths that light can repeatedly take. The limit of intuition arrives with a calm correction. It is tempting to imagine a clean wall that blocks everything at a certain radius. The horizon is not a wall. It has no texture or colour. It is defined by which paths can still reach far away. Near it, time behaves in ways that resist everyday intuition. Emission from very close regions can seem delayed and dimmed. It can appear to linger and then vanish. The limit is that delay and fading do not reveal what happens after crossing. A small payoff settles. Delay and fading are a signature of the boundary. They are not a window through it. The limit of observation arrives next with practical detail. A sharp halo and a deep deficit can be produced by more than one arrangement of the surrounding flow. A thicker haze can blur the inner edge and imitate a larger deficit. A thinner haze can sharpen the edge and imitate a smaller one. Curved paths can create brightness peaks that resemble a tighter ring even when the emission region is broader. Finite resolution blends beads into arcs. It also blends arcs into a smooth halo. The limit is degeneracy. Different conditions can produce similar images and similar light curves. A small payoff follows from that limit. Confidence comes from combining many kinds of evidence. Geometry variability and spectrum must agree in a consistent story. The scene eases outward again. The halo becomes fainter. The brighter arc softens into a gentle crescent. The deficit remains quiet and stable at the centre. The outer haze fades into the surrounding darkness. The physical detail of gradients becomes softer. Sharp edges become gentle slopes. The last scale shift widens into the calmest frame. Over long times, inflow and outflow can wax and wane. The boundary remains as a simple rule. Some paths escape, some paths do not. A small payoff lands as the arc resolves. The title question finds a settled answer. Near a black hole, much can be observed in the outside flow. The boundary itself is inferred through patterns of light and time. Beyond that, boundary observation ends by definition. The closing image holds steady without suspense. A dark centre rests within a thin, curved glow. The glow dims into a quiet, even night. The next moment is not a new mystery. It is a gentle stillness that remains.